Swayam Prabha. Digital India. Educated India.
Good morning, everyone.
Good morning, sir.
Namaskaram. So, we will start this particular lecture. So, as the student has introduced, I am Chaitanya. My group works in the areas of computational chemistry and material science. How many of you heard of the word computational chemistry earlier? Okay. Some, not all. Okay. So in this lecture, what we will see is we will try to understand how do you compute few electrochemical properties of anode materials. Okay, so here specifically we are trying to understand about 2D materials that can be seen as anode. So before going to this particular lecture, I will just try to briefly introduce you to some topics of the quantum mechanics. I think some of the lectures might have covered and touched upon some aspects. We will just interact for a few minutes about that, such that you will be able to appreciate a little better about what we are going to deal today. Okay, how many of you have done anything about quantum mechanics? I mean, anything that you heard of? Just raise the hands and you can just give me some hints of what you have learned or heard.
Energy levels are quantized in quantum mechanics.
Energy levels are quantized. Uncertainty principle you heard of, yes. Anything else? Energy in G. Qubits, okay. You heard of qubits, and the superposition principle you heard of, okay. Anything else? Schrödinger's wave equation you heard. Time dependent and time independent Schrödinger equation. Anything else? So these are actually very good points that you have started with. To some extent you guys know. So essentially, what is the story of quantum mechanics? You heard of, what is the story that you know? Black body radiation you heard of. What happened in the black body radiation?
He was getting it. Classical mechanics could not predict it properly. So when you quantize energy levels,
Classical mechanics I think predicted that
infinite.
Yeah, if you go to infinity, but it fell back now.
How many degrees of freedom will be?
So you might have seen about this Rayleigh-Jean's law, Wien's displacement law, and other things. Again, if you did not see, it's completely fine. The story is essentially this. So when you go down, in terms of atomic picture, when you try to see, you are unable to explain based on the laws of the classical mechanics. What are the laws of the classical mechanics that you studied? In your +1 itself, you have studied definitely. Newton's laws of physics, that's all you have studied. What are the Newton's laws telling you?
Inertia, momentum,
Rate of change of momentum is equal to force, okay. Action and reaction, okay. Every action has an equal and opposite reaction, So you understood at least, based on the classical mechanics, if someone tells you the positions and velocities of an object or the group of objects at time t equals to 0, you will be able to apply the Newton's principles or Newton's laws, and you can tell deterministically what will happen to those group of objects after time t. All of you are with me?
Yes, sir.
Okay. So if I have a group of objects, or at least a simple object like a tennis ball or something you have in your hand, and if I tell you what is the initial velocity of this ball and where is it situated at time t equals to 0, using the Newton's laws of motion, I will be able to tell where it will be after time t, subject to the forces that it is experiencing. It could be electromagnetic force, electrostatic force, or you can have gravitational force, frictional force, this one, that one. These are all the different problems that you are solving. But essentially what you are doing is, you have something at time t equals to 0 and you are going to predict at time t equals to t. And throughout this process what you understood is, okay, if I am applying these Newton's laws, I will be able to tell anything about the system. And based on these positions and velocities, in general you are able to tell any property of the system. For example, if I wanted to know the angular momentum of an object, what is the formula that you learned for the angular momentum of an object? R bar cross P bar, right? That's what you have learned. So P is nothing but what? Momentum. So that means if you know the velocities or momentum, in either way, people use them interchangeably. Let us call them positions and momentum. So then you know R is nothing but the position, P is nothing but the momentum. Now, if I need to calculate the torque, what I need? R cross F. And F itself is written as dp by dt. So if I know the change in the momentum and the position, I can calculate the torque. Rotational energy. Have you heard of rotational energy? Whatever it is, at the end it will become as L square by 2I, or whatever. L is like, if I consider R bar cross P bar, it will become L square by 2I. 2I, I has again M R square. So R is nothing but the position, M is anyway the mass of the object that you know by. That's the reason you are able to calculate the momentum in the first place. Again, you are able to get the energy. If it was simple kinetic energy, what it is? Rp square over 2m. The moment you know the momentum, you know the kinetic energy. Similarly, potential energy, if I need to know, you will be writing, if it is a gravitational one, mg h. H is nothing but again position from a specific thing. If you know the position of the object, you again know the potential energy. If you know the kinetic energy and the potential energy, what you know? The total energy of the system you know. So like this, if you take any property, classical mechanics essentially is trying to give you that property in terms of positions and velocities. This topic probably will be covered, or will be covered at a later stage, is called as the phase space. Okay, so the moment you know x's and p's, or positions and momenta of the particles that are associated with any system, classical mechanics will allow you to calculate that particular, the trajectory of the system, whatever it is going to behave like, you will be knowing according to classical mechanics. So this is the, what you call, somewhat solid foundation based on which people started exploring everything in classical mechanics earlier, right? Like whether it could be planetary motions, or whether it would be about the behavior of the atoms or molecules or something. Everyone tried to explore everything based on this positions and momentum, based on the Newton's laws of motion. So somewhere in between, light also came, and our Maxwell was the great person who united the light theory and this magnetic theory, and electromagnetic theory came to you, and so on and so forth. So this is like a complete picture by the end of the 19th century, that you are okay, like we felt that more or less we know everything, how to calculate, etc. It might be difficult for us to calculate for bigger systems, or it might take for intricate details might be there in order to calculate for specific systems, but everyone felt that we know everything. Okay, this is what is the picture. It's only required, like, okay, 12 years of schooling is required in order for you to learn everything about it. After that, you will be able to solve any problem that is given. This was the idea. But then this idea was shattered once this black body radiation was started. Okay, so these were again experiments. People were trying to explain how these experiments were happening, and they were unable to explain this black body radiation using the classical mechanics, principles of the classical mechanics. Then, as you all heard of, Planck is the guy who said that, okay, what he did essentially is today's machine learning kind. Okay, so he fitted the data and he identified a formula, and he found that that formula is actually working. This is exactly the truth. There is nothing exaggeration here. Okay, so he saw this distribution. This is nothing but the energy distribution. If you remember that plots, whatever were there, energy versus the wavelength, how the energy is emitted by a black body radiation with respect to the wavelength is what they have seen, and they identified that, oh, this is the kind of distribution I have. If I am applying this particular formula, I am getting something like a catastrophe. Ultraviolet catastrophe is the one that you guys are trying to explain. Something went like this. Another guy came and they found that this is working for this for high frequency. Another one's formula is working for low frequency. Oh, something is missing. Let me try to put this particular equation and check. He checked and he identified that it is working for all the frequencies. So this is only feasible if you are quantizing the energy. But that particular thought itself is something new at that time. What is new there? Energy is quantized. Do you agree? Like if I am saying that energy is quantized, on a classical level, on a day-to-day basis, when we are interacting with the surroundings, environment, why should we believe that energy is quantized? What does that mean? It means, for example, how many of you rode any motorcycle or just scooty or something? Okay. Some of you have this experience. Many of you have drove at least bicycle, right? So if I say that when you are driving the bicycle or riding the bicycle, when you do this pedaling, first time you will go up to like speed of 10 kilometers, suddenly you will go to 20 kilometers. Will you be able to accept this? You start pedaling, 10 kilometers is the normal speed, immediately next step is 20 kilometers, the next step is 30 kilometers. Will you accept this? No, right? Like you will always expect that the energy is continuous, or in this particular case, the speed is continuous. It will be like, oh, if I am starting with 20, I will be slowly increasing to 20 point something something and then leading to 21, not directly from jump from 20 to 30. Yes or no?
Yes.
Yes. So this is something, a new idea. Whether you are able to accept, if you are accepting it, that's a different story. But if you are asking as a question, you need to see whether it is actually a reliable idea or not. Okay. So that's why people did not take it as something very important. When Planck tried to introduce this idea, people accepted it as a technique, but not as a truth. Okay. So then Einstein saw this particular point and he applied the same to what? Photoelectric effect. So please remember the story there. Okay. So this was first given as an idea, energy is quantized. Einstein said that, okay, not only for this particular case, I will use it for the light being quantized, having h nu, photon. Every photon has some specific energy. This is what he has used, and he was able to explain the photoelectric effect. This is again, one experiment was done, people were unable to explain it, and when you used this concept of energy quantization, immediately you are able to explain that particular experiment. This is not the end. Someone else came and asked about this Bohr. For example, the Bohr's model you might have studied in your +1 or +2, I don't know which level it came. There, what Bohr did is, these guys said about energy quantization, he used it for the angular momentum is quantized. Angular momentum is quantized. Just now I said that if I say that velocity is quantized, will you be accepting it first place? No. But someone now started that angular momentum is quantized, and that's how, if you remember, MVR equals to NH cut or something you will be using there. Using that you are able to explain the hydrogen atom problem. That Balmer series, Paschen series, Fund series, etc. All these series, everyone gave one formula, but this guy just by using one particular point, that is angular momentum is quantized. This is what he thought. And the moment he applied this MVR equals to NH cut, what he was able to do? He was able to get a uniform formula for all the hydrogen atom spectra. That means all series, he was able to give one formula. Okay, and he has proved it through something. But is that the final thing? Again, there were some other quantizations people were able to, what guess? These are all guesses. Nothing is proven till this date. Okay, till Bohr has proposed MVR equals to NH cut, there is no official methodology. Einstein guessed, Planck guessed. Oh, these two guys thought that energy is quantized. This one is quantized. I will also think that this is quantized. This is the way it went. Are you able to understand and feel about the story? So someone said that, okay, there is that thing, it will work. So this person said, okay, I will use that one also for this. That's all. It's like pretty randomly they have done till that time. Fortunately, it started working out. Therefore, people started celebrating it. Okay. Then came Schrödinger. So this is the place where actually de Broglie has proposed about this wave particle duality. Someone called Debye, is like a little big figure at that time, asked Schrödinger, see, this guy has proposed about this wave particle duality, you are very good at wave mechanics, why don't you see and try to apply it for this? This is how Schrödinger went and sat and he worked out on the equations, and he finally came up with that, what you are now knowing as the time independent and time dependent Schrödinger equations. Okay, so this story is important for you to remember, only memory. You will again read about each one of these topics carefully. The point why I am trying to tell this whole story is energy quantization and Schrödinger equation. These are all one step like that. This has come. It's not that Schrödinger equation was coming like this. Okay, so there were several series of experiments that were done earlier, and people were trying to understand various concepts, and some people stumbled upon this quantization approach and it started working out. Therefore, someone tried to create a theory which will explain everything. Okay, so for that, Schrödinger is one particular person who tried to explain it through the wave equation. You might have heard that Heisenberg is another guy. Instead of the Schrödinger's wave equation, there is another thing, Heisenberg's matrix mechanics. He has tried that way in order to again explain the quantum mechanical principle. That is again another approach to quantum mechanics. One is called as wave mechanics approach, another one is called matrix mechanics approach, and both these approaches will be able to explain the quantum mechanics properly. Okay, so now why I said all these things again is, for me, whatever I am doing right now computationally is all about solving the Schrödinger equation. Okay, I will be solving essentially the Schrödinger equation in order to say anything. Okay, so let's see what all are there. So before starting, so these are the three people who, I mean, of course there will be many mentors, but these are the main ones just before coming here. So for you also there will be many teachers. So I did my PhD with Professor Swapan K. Pati. With him I have investigated a few low dimensional systems. So these are nanomaterials, if you heard of the nanomaterials. I have studied something called graphene quantum dots, graphene 2D systems, as well as borophene and various other layered materials, as well as quantum dots with him. And I have calculated what is known as the electronic, optical and various other properties on computers by solving this time independent Schrödinger equation. With Frank, I mean his name is Peng Phi Huo, but his English name is Frank. So with Frank I have worked on organic photovoltaic systems, and I have developed what are called as the non-adiabatic dynamics techniques. Okay, so these are useful in order to study the charge transfer phenomena. The moment you shine the light, for example, the light is shining on the chlorophyll which is present in the leaves. Okay, through that there will be, you all learnt about how water will be taken by the plants and how oxygen and carbon dioxide cycles will be there, etc. Right? So all this is happening because of the light, photosynthesis. That much at least you might have studied, right? So that whole process is nothing but what you call mediated by the light, but it involves the several charge transfer events. If you read about this oxygen evolving complex, oxygen evolution complex, that's the place where this oxygen will be evolved. So such kind of things we have studied specifically for organic photovoltaic systems. Okay, finally I went to Brian. With Brian, I have used this ab initio molecular dynamics and electronic structure methods in order to study various kinds of problems, for example, catalysis or degradation of water pollutants and so on and so forth. Okay, so these three people have mentored me, and in general, you people feel that teachers are the one who will be teaching and students are the one who will be learning. But the moment you become professors, you will realize that you will learn a lot from your students. While teaching also you will learn a lot. So these are the PhD and the postdoc students who are working with me. Specifically, this particular presentation that I am presenting is a work done majorly by Subhadeep, but also to some extent by Ankita. So these two people I would like to acknowledge for their things. Of course, like when I am presenting here means there will be various other funding resources, etc. Of course, IITM is the major thing. In addition to that, we have used the computational resources from both the IIT Madras as well as from the IIT Kharagpur, and there are various other funding resources like CQuIC, CAMD, etc. These are the centers. So with that, I would like to just introduce you to few research areas that we work on. So the first one is, again, as I said, about the charge transfer dynamics. So what is this? So you can see here, this is what is called as a fullerene molecule. How many of you heard of the fullerene molecule? Wonderful. So fullerene is a very good acceptor molecule, okay? And this one, what is there below, is called as a phthalocyanine. You know, like chlorophyll molecule has a porphyrin unit. So this one is slightly different than that. So this acts as like a donor and fullerene acts as an acceptor. So what we are interested in studying in this particular project is to understand, after you shine the light, how the charge transfer would occur between them. So just in this cartoon or in this specific figure, you can see that this is nothing but the electron distribution or the electron density. At the initial stages, this is the donor. So the electrons are present in the donor. As the time progresses, slowly the electron cloud is slowly moving away from the donor, finally reaching the acceptor. So this is something done based on the time dependent Schrödinger equation, because there is something that is happening in time, which is happening with respect to time. So therefore this can be solved only using the time dependent Schrödinger equation, and this is one kind of an application of the computational chemistry. So you can use computational chemistry to simulate charge transfer dynamics in organic solar cells. Of course, inorganic solar cells, any other solar cell you wanted to understand, you can use computational chemistry. There is no need for you to go and only do the experiments. You can also do the same thing using computers. This is one kind of an example. Second area that my group works on is the energy storage. So this is the topic that we will be discussing a little more deeply, which is identifying the anode materials of a battery, okay, that I will tell little later. The other part is about the solid electrolyte interface. So all of you are aware of a battery material that is there in your mobile phones, etc. So battery typically consists of an anode material, a cathode material. There will be a electrolyte as well as a separator, which will be allowing the ions only to pass but not the electrons. This much knowledge all of you have? Yes? Okay. So what happens in general is, when this electrolyte comes, during the charging and discharging, ions will be passing through this electrolyte, but this electrolyte will come and interact with the anode as well as the cathode materials. In general, when the anode material is there, this will come and interact with it, and the electrolyte starts to decompose. Okay, anode will have a lot of electrons available with them. So these electrons can either, oxidize or reduce. In this particular case, let us assume that it is reducing. All of you know what is reduction and oxidation, right? Addition of electrons is called reduction. Okay, so some of you also said reduction. Okay, so this is essentially reduction. So what it is happening, you are adding the electrons, therefore the bonds can break, right? So when you have more electrons than what is necessary for the bond will break generally. That's what, like, the moment you are decomposing these molecules, they will act like a passivating layer. So you are aware of the rust that forms on the iron. You know that it is nothing but iron oxide also, that is acting as a passivating layer or a coating layer on top of this iron. What it is helping it? It is helping it to stop further rusting. Are you able to feel this? So you have a pure iron there. What happened? Oxygen that is present in the air is coming and interacting with this, and what is happening with that? Iron oxide has formed. This iron oxide is bad for the iron. However, what is helping it? It is helping it not to rust further. It is acting as a passivating layer such that the lower iron, whatever is there, that is protected now. And this you will see everywhere in normal any particular material you see, there will be some kind of a layer that will be forming, which is like corroded or something like that we feel, but it is also acting as a passivating layer. So similar kind of thing will happen even in the electrode systems. So where the no. Okay. So what we are saying is, this is actually not the solid electrolyte that you are thinking of. What I will explain you slowly. So what you need is what? You need actually the electrolyte for the ions to conduct. Electrolyte is for what? Electrolyte is for the ions to conduct. So when you are saying gas is there, from where the ions will conduct. There should be some channel for the ions to move from one place to the other. You can send the ion in the gaseous phase also from one place to the other place, but there is something called conductivity. So you wanted to improve the conductivity such that when you are seeing the outer circuit of this electrochemical cell, outer circuit of your battery, what you will be doing on your mobile phone, you are touching with the screen, right? Like on the touch screen, when you are doing what it is happening, you are using the electrons, right? That's how you are able to change the voltage. So first you have charged your battery, that means you created some voltage difference, and then when you are pressing it, this voltage is slowly becoming like this, such that the battery is drained, right? When your electrons are going in the outer circuit, ions have to go through this circuit inside. Outer circuit means like your battery outside, whatever you are doing is the outer circuit. Inside, the voltage has to come back, means like ions have to move. So I will show you the principle, then maybe you can ask more questions that will help you to understand. So here, what I am trying to tell is about the solid electrolyte interface. What is the solid electrolyte interface is that liquid electrolyte that she is mentioning. Liquid electrolyte can be simply, you can think of water, but organic electrolytes are what is generally used in our mobile phones. These organic electrolytes are like ethylene carbonate, propylene carbonate, etc. These are like cyclic compounds with carbonate is there. So these molecules can decompose and form like a passivating layer. So specific to the lithium ion battery, this passivating layer is very advantageous because, as I said earlier, it will help to not corrode further. That electrolyte decomposition, it will stop. Moreover, the lithium ions are very small. You know that hydrogen, after that is lithium. The smallest atom that you know is hydrogen. After that is helium. Anyway, that is an inert gas. After that you know is lithium. So because it is a very small atom, it can actually go through this decomposed electrolyte and reach towards the other side. Whereas this is also an insulator. How many of you are aware of the insulator? What is an insulator? Something that doesn't conduct the electrons. So here what happens is, electrons are no more conducting. As I said earlier, electrons are coming from the anode material and going on to the electrolyte, and it is decomposing this electrolyte. So now this passivating layer is acting as an insulator. Therefore, the electrons that are coming from the anode are not going any further and decomposing, rather they are stopped here. But the advantage still is this lithium ions are very small ions. They can still pass through this particular solid electrolyte interface and go. While this is very good with the case of lithium ion batteries, if you study any other alternate ion batteries, sodium ion batteries, magnesium ion batteries, calcium ion batteries, etc., you don't have that advantage. So this is another area that our group is studying and working on, how to tune this solid electrolyte interface such that it can be beneficial for the batteries. Okay.
So in the first charge started for batteries, you said you run simulations to check how it works. So sir, how exactly do you make the simulation? Because there is software package. What software?
Okay. You have another question? Okay. Yeah, you are saying something.
Yes.
Same question. Okay. So the question that they are asking is, how do we simulate this particular one? That's all, right? Okay. So for that particular case, we have used certain software packages as well as we have written codes in order to do the simulation.
Sir, how do you know, like if you already know what's going to happen, then what's the point of running the simulation?
Very good question. So what is going to happen is only known to us in terms of like, this is a donor, this is a acceptor. What is the time scale in which this transfer is happening? Number one, this I know when the interface is like this. When the interface is, two of these molecules are there, one fullerene molecule is like this. But is it the case in reality? In reality, this will not be the only acceptor, this will not be the only donor. I have thousands of acceptors, thousands of donors. For example, non-fullerene acceptors also exist for me. And interface means like when you are considering, this is like a bulk heterojunction, if you heard of this word. These are not like just coating of, okay, one layer of acceptors are there on top of which I will keep one layer of donors. These are like miscible in various proportions. How do you simulate such kind of systems is the first interesting part. Okay. Second thing, I mean, for the simple cases, if you are considering, you have 10 different acceptors, 10 different donors. What are the time scales in which this charge separation will happen? Why I need about the charge separation is, if I can efficiently separate the electron and the particular hole there, that means I am able to separate the charges. That means I will be able to use them to create the potential. So this can become like an energy storage device.
So how do you know that the simulation results are like, true in reality?
You can, of course, like always there is a way for you to check with respect to the experiments. So you can conduct the experiments, I can conduct the simulations and I can check. But there are different levels of benchmarks within the simulation itself. So when you are doing everything at the quantum mechanical level, you are very sure that that is almost close to the perfect. Okay, but simulating these things using quantum mechanics is not something that is straightforward. Okay, it's not that easy as it sounds like. Okay.
For that CD dynamics, you use the quantum chemistry package, but it's in Newton.
So yeah, I have used what is called as density functional tight binding theory. It's a package also called DFTB, but that doesn't have simply to you to run it. I have to rewrite the code to a certain extent. I have done that during my postdoc time. So there are certain methods called fuse switches, surface hopping and other things. These are non-adiabatic dynamics methods. I'll try to show you a little bit about that and then you will be able to appreciate. The package that I used is DFTB plus, but a modified version of the DFTB plus. In-house modification was done for that. But nowadays there are packages. This work I did in 2016 or so. So now there are packages that help you to do the simulation without writing the codes. I mean, they have already written the codes. You don't need to write the codes. That time there was not something available for me, so I had to write the code. But there are now codes that can simulate those things. Okay. Any other questions? Yeah.
So what kind of information do you get in a solid Schrödinger?
You will get any information that you want.
So
As in like, for example, as we discussed earlier, if you know the positions and momenta of a particular system, what can you calculate? The answer is anything that you want, you can calculate. Similarly, when you are dealing with the Schrödinger equation, what you are going to get is the wave function. According to quantum mechanical postulates, if you know the wave function, you know any information that you want about the system. Okay. In that context, I said that anything that you wanted to. Okay. But every simulation, you will be doing certain things in order to achieve certain properties. Okay. Again, I will show you some properties that we wanted to. So the other one is about the degradation of the water pollutants. Again, I'm trying to introduce you to the areas. The reason is you will be able to appreciate what all different kinds of things that you can simulate. Okay. Don't just think that, okay, this is the only point I can simulate. In order to avoid that only, I'm trying to show what all different things that we simulate, but this is only a very small spectrum of what can be simulated on a computer. Okay. I'm just showing the diverse areas that my group alone is trying so that you can appreciate what others can do easily. Okay. So this one is about the water pollutant degradation. The one that you are seeing here are called as perfluoroalkyl substances. So do you know, guys know what is the bond dissociation energy of a CC bond or a CH bond by any chance? Any guesses? You are smiling a lot. Can you tell something? I am not making any jokes, but it looks pretty funny to you. Okay, fine. Anyway, so one of the strongest bonds that you can think of with carbon is the carbon-fluorine bond among the different kinds of bonds. So if you consider CC bond versus CH bond, the difference between them will be around 30 kilocalorie per mole, where CH bond is stronger when compared to the CC bond. And when you compare CH bond to CF bond, another 30 kilocalorie per mole you can think of, and this will come around in hundreds. So the CF bond is the strongest bond that can be formed between a carbon and any other element in the periodic table. So from this, what you should remember is the carbon-fluorine bond is something that is not available in nature. This is a man-made bond. Carbon-fluorine bond is a man-made bond. And the perfluoroalkyl substances are nothing but, you know what is a hydrocarbon, right? Hydrocarbon is nothing but anything with CH kind of bonds you are calling as the hydrocarbon. If you replace the hydrogen atoms of this particular system with fluorine atoms, it is called as perfluoro or polyfluoro. If you are not replacing everything, it is called polyfluoro. If you are replacing everything, it is called perfluoroalkyl substance. So similar to in your organic chemistry, you might have studied so many varieties of hydrocarbons. So all those hydrocarbons are possible with respect to the perfluorocarbons also, because essentially you are replacing hydrogen with fluorine, that's all. So it's very easy for you to take any number. So because of this strong carbon fluorine bond, these perfluoroalkyl substances have wide variety of uses. For example, you might have heard of this name called Teflon. Yes, so that is actually a polyfluorocarbon containing system. It's a polymer essentially, and that polymer, you see that you will be using it on whenever your water leakage is there, you will put a Teflon. Teflon is also used for other kinds of coatings, etc., etc. In aviation industry, you will see that Teflon is heavily used. The only difference is like the Teflon is not that much easily soluble, so they will add what are called as this perfluorooctanoic acid or sulfonic acid, these kind of smaller systems, and they will be used in, for example, you heard of this non-stick cookware, right? So on the pan, if you touch it, it will be very smooth. You put a water droplet, it will be like your what do you call, lotus leaf, right? It will be just that one will be there with that hydrophobicity. You put the oil also, it will be like this, right? So this is oil repellent as well as water repellent character is there. And if you wanted to extinguish fires, so the firefighting foams, the firefighters, if you see, they will use this perfluoroalkyl substances. Textiles, if you wanted to have some rainwater coat, that will have these perfluoroalkyl substances. So whatever you are imagining, majority of the things, like even if your popcorn is there, like if you put it in the microwave, that bag that will come, that will have this PFAS coating. Okay, so wherever you wanted to store for a long time, wherever you don't want to degrade anything, textile, paints, aviation industry, food packaging, you name anything, you will be seeing this perfluoroalkyl substance. Just one second. So this has quite ubiquitous use because of this strong carbon fluorine bond. But as I said, this is a man-made bond. This is not available in the nature. Therefore, when you start consuming these perfluoroalkyl substances, they will start to accumulate in your body. Okay, not the very long chain ones, but the small chain compounds, like the 8 carbon or 10 carbon, if you are considering, they will be able to accumulate in your body, and they can replace the existing hydrocarbon, some protein, something they can change, and they will cause various kinds of illnesses. So very good. So he studied something about it, and it's a good thing. Okay, so the point that I'm trying to tell here is, whenever we are introducing something into the environment, like in the beginning, what we will be trying to see, we will try to see the applications. The applications of PFAS are huge. However, at the same time, we are spoiling the entire environment. Right now, the entire environment is polluted with PFAS. Okay, its influence is so large that if you go to Antarctica, also you will be able to see the PFAS. And its contamination is so bad that if you see an infant drinking the milk from mothers, they are also, even in mother's milk, you will see the PFAS. So this is the range of contamination that PFAS is already there all over the globe. Okay, while we are sitting here silently, we are not aware how much levels of PFAS are there within our body. But if we test, most of us will have the PFAS. I'm saying in a liberal way, all of us should have the PFAS inside us. Okay, so that's the situation that we are there. Recent studies from IIT Madras, from the civil engineering department for the Adayar river, has very high levels of the PFAS. Okay, so why I'm saying all this is, like, there are like certain times, like we feel that whatever we are inventing, etc., will be very important. It will be important, it will be useful, but we will forget to see how it will be going to impact the environment. This is the area when you study as sustainability. This is something that you need to understand, that whatever we are inventing, we need to be more careful. Earlier, whatever we use it to have, they are more sustainable. Like, it might not be very efficient, but they are very sustainable. But what we have created, as all of you know at least about the plastic usage, right? We created the plastic and now we are banning. We created the PFAS, now we are banning. We created something else, we are banning. So we should be a little bit more cautious is the point. It's not that you should stop the scientific innovation and go back to the old age or something. That's not what I'm trying to tell. But we should be more careful about the effects that it can bring. So in our group, we are trying to see the ways to degrade these perfluoroalkyl substances. One such way is to use the nanoparticles and use the plasmons. How many of you heard of the plasmons? Plasmon. Whenever you see on, electron, proton, photon, etc. They are particles, right? So they have the particle nature. So you all know that every wave, according to the wave particle duality, every wave will have a particle nature and every particle will have a wave nature. So plasmon is like the collective oscillation of the conducting electrons of a metal. Okay, so corresponding to that there will be a particle nature. That's what you are referring to as the plasmon. So this is like a quasi particle. It's not like a true particle, but it's like a quasi particle that will exist when this motion is there. When this motion ceases, that particle also ceases. That's the way it is. So we are trying to use this plasmon induced degradation for the PFAS. Also we are trying to use various kinds of metals as well as electron means like reduction, oxidation, etc. through various materials to degrade this substance. Here we are showing like the electrons are added to the PFAS and how the PFAS is decomposed into various fragments. That's all is the picture is suggesting. Recently we are also started utilizing quantum computing. So there is like you might have had 1 or 2 classes about quantum computing. So what we are essentially doing here is, till now we have the classical computers to simulate all of these compounds. But quantum computers are offering a new way to simulate the systems. We have started simulating small molecules on these quantum computers and trying to see how can we solve the Schrödinger equation, how can we solve bigger molecules, etc. We are developing the algorithms corresponding. Okay, so please see here. So what we are trying to do here is we have any system that you are considering that can be seen as a bunch of atoms. These atoms you can see, atoms contains what? Nuclei and electrons. So you can see that there are m number of nuclei and n number of electrons that are interacting with each other. What kind of interaction between a positive charge and a negative charge? Electrostatic interaction. So in order to solve any system, I can utilize 2 kind of equations. All of you told already these equations. First one is called as the time independent Schrödinger equation. Second one is called the time dependent Schrödinger equation. First one is called as the time independent Schrödinger equation. Second one is called as the time dependent Schrödinger equation. So what happens is, in the time independent Schrödinger equation case, you can think that, as I said earlier, you have a bunch of nuclei, electrons interacting with each other. So first I will assume that the nuclei are fixed and I am trying to understand the optimal positions of the electrons. So while I am saying optimal positions of the electrons, you can think that electrons as like particles and they are there. The better way to describe this is, when you are solving the time independent Schrödinger equation, you are fixing the nuclei and you are trying to understand the electrons distribution. Okay, so you are trying to optimize the positions of the electrons or optimize the distribution of the electrons. The difference between position versus distribution is, position you are thinking still in the classical picture, whereas when I am saying distribution, it is the probabilistic nature of the electrons I am trying to say. That's the reason I am saying the distribution of the electron cloud. Instead of thinking of each electron, now you are thinking in terms of the electron cloud that is distributed. So these methods are called as the electronic structure methods. So you are essentially identifying what is the structure of this electron cloud, okay, about this nuclei. So you have the nuclear coordinates are fixed, you are assuming, and how this is behaving is the question that you are asking.
Optimization as in minimizing repulsive interactions.
You can think that way. Okay. Yes. Optimization in the terms of like minimizing the whole electron cloud such that the total energy of the system is going low. Okay. So that's all is our aim. Like, what is the most stable state? How can I create the most stable state is what you are solving when you are solving the time independent or time dependent Schrödinger equation. So here this problem is also called as the eigenvalue problem. Hψ is equals to Eψ is also called as the eigenvalue problem. That means what you are essentially doing in this, generally you remember this Hψ equals to Eψ. I'll come back little later in next slide itself. The second scenario that we will be generally solving is for the moving nuclei. Okay, so as I said, in the time dependent phenomena, whenever you consider the time dependent phenomena, you have one case is like only the electrons are moving whereas the nuclei are not moving. There is another case where both the electrons and the nuclei are moving. Okay, so you know the forces, right? So when electrons are moving, electrons can exert force on the nuclei. Similarly, when the nuclei are moving, nuclei can exert force on the electrons. This interactions between both of them can lead to a complete motion. That motion is what is captured through the time dependent Schrödinger equation. Okay, again here there are multiple versions of movement or the dealing. The highest level, at least I mean to the extent that we deal with the highest level, is treating everything quantum mechanically. That is both the electrons as well as the nuclei quantum mechanically. When you deal, that's when you call it as a quantum dynamics. Okay, so whatever I said, what does it mean? So when I say about a molecule, what is the picture that you have in your head? For example, CH4. What is the kind of picture that comes to your hand? Some tetrahedral ball and stick model is what you are using, where you are keeping the balls as nothing but the hydrogen atoms and the carbon atoms, and then bonds you are thinking as some sticks or something like that. This is what you are thinking, imagining. But this imagination itself is again further wrong, because we are saying that this is a molecule. Is molecule a quantum mechanical object? The moment it is a quantum mechanical object, can you define a specific position to it?
No.
Based on the uncertainty principle, you are clearly aware that delta x, if you are trying to keep 0, then delta p will become very high, right? At least. So it is undefined in the other way. So therefore, what you should have a picture of a wave for that. Okay, that we cannot have. Oh, that means it has to move like this, up and down, etc. Right? So when we are saying that quantum mechanically it is there, it is already proven through experiments that superposition principle someone said, right, in the morning, I think you said. So the superposition, so if you consider the methane molecule and if you try to send it through the double slit experiment, that means with 2 slits, if you are sending a bunch of methane molecules, you will see that they will also show you this superposition. Okay, and people have proven it for fullerene molecules, even bigger macromolecules. So all of them are in superposition. They are not there as individual molecules that we are thinking, we are imagining. Okay, so that is the quantum dynamics level, where the nuclei, that atom that you are considering as like a ball and you are fixed way you are seeing, that's not the way that we deal with. Rather, you will deal with as a wave. That means how we are representing the electrons as psi. Psi is the wave function representing the electrons. Similarly, if you represent the entire molecule as psi, that is a wave. The moment you represent the entire molecule as wave, and if you solve the time dependent Schrödinger equation, that is called as the quantum dynamics, because everything is quantum mechanical here. The next level is mixed quantum classical. The word itself has the whole meaning. Mixed quantum classical. So what is classical? What is quantum? If you start imagining that the nuclei are, because they are little heavy particles when compared to the electrons, if you assume that nuclei are acting like a classical beads or some balls or something, and if you are giving a specific position and momentum to them, whereas electrons are treated quantum mechanically, this is called as mixed quantum classical dynamics. The next level is obviously classical dynamics, where you are assuming that electrons you are considering as point charges, and you will use the electrostatic relations in order to solve the dynamics of this one. That is called as the classical dynamics. Some quantum mechanical effects can be kept inside this classical molecular dynamics also by some fitting parameters, etc., etc. So this is what you will be learning if you are going to do computational chemistry anytime. This is what is called as force field methods or classical dynamics. Okay, So there are these three sets. In between there are other ones. They are called as semi-classical dynamics. These are also very important. Mixed quantum classical, as I said, complete classical. Therefore, these are the different varieties of the dynamics. In addition to that, the dynamics itself is further divided, okay, into adiabatic dynamics, non-adiabatic dynamics, etc. I will come to that little later. So now let's focus on the first part. So what is the first part? Time independent Schrödinger equation. It is called as the H psi equals to E psi. That is an eigenvalue problem.
Swayam Prabha. Digital India. Educated India.